Okay, Assalamualaikum and good day everyone. So this is the lecture continuation from last week. Um, we have done example 1, 2 and 3, and then for today I would like to present to you, demonstrate to you the example 4 using the root locus to design the PI, PD and PID controller. For today, we will do example 4. Alright, the question for example 4. Design a PI, PD, and PID controller for the following plant, where we have the plant, in this case, is a GP equals to 0.7 over S plus 3, S plus 1, and S plus 0.3. So we'll use all this controller, all this plant to make a controller as listed in the question. And then the design requirement for the controller is to improve the system response. Such system response has the peak time less than 3 seconds, and percent overshoot less than 10%, and steady state error for a unit step input is less than 1%. Okay, let's start with P controller. Okay, what we need to do is that we plot the root locus of the plant, and using the seesaw tool, we'll find the gain that will give 10% overshoot, and basically this will happen at if you select KC equals to 2.4, you will get TP at 4.7 seconds. So it failed to meet the peak time requirement. In this case, we want the peak time requirement must be less than 3 seconds, as per example, as per the questions. Okay, and then if we select the TP to be 3 seconds, we will fail to get the 10% overshoot. Okay, and let's try to do that in MATLAB. Okay, let's do this. Alright, so we have the GP, we will use ZPK, and then we will call for seesaw tool function. Oh, sorry, this is GP. So call the seesaw tool function, and the control system designer window will appear, and you wait for the plot to come out. So what we are interested in this design for now is we would like to have the root locus as well as the step response for the system. Okay, what we want is we want to see the peak response and as well as the steady state value. Okay, this is the original system, and basically we want to have the C. Example, we have the P controller. We decided to use C at 2.44 seconds. Sorry, 2.44, which in this case, maybe I will try to use this view. Alright, we will use the float view, and I will show you. Okay, this is the response, the step response. to the P controller where we set the KC equals to 2.44. Okay, so we get the 10% overshoot here, but the time here is 4.68 seconds, which is not meet the design requirement. The design requirement needs you to have TP at 3 seconds. If we set the C to 6.2, the KC to 6.2, what happened is that we can get the time here at 3 seconds, the TP at 3 seconds. However, the overshoot will have 33%. So it's far greater than the design requirements for the questions. So that's it, what we can do for the P controller. We cannot get, if you can see the final value as well, the final value is about 0.83. So we have a steady state error greater than 1%. Also does not meet the design requirement. In fact, if we set to 2.44, the KC to 2.44, we still get the steady state value, which is here, is 0.655, which is far greater than 1% steady state error as per requirement. Okay, now that's it for the P controller that we can tune. So now let's see for the PI controller. Okay, for the PI controller, let's choose the 0 to cancel the smallest pole of the plan. For example, here we have the plan. Here we have 0.3, -1, and -3 for the pole. So let's cancel negative 0.3 here. So we select the ZI is 0.3. So for the PI controller, so basically for the PI controller we have a KC which is equals to S plus ZI over S. Okay, so we select ZI equals to 0.3, so we will get S plus 0.3 over S. Okay, so we try to adjust the chisel tool here. So we add an integrator, because the PI controller we introduce integrator, and we have a 0 at negative 0.3. Here we have let's change to the setting for this. The option must be 0 pole and gain. Okay, so we have here 0.3. Okay, when we set the system to be 0 S plus 0.3 to cancel out the pole for the plant, and then we set the KC equals to 2. So what we get here is we get the overshoot is 8.94%, which is less than 10%. However, the time peak here, what we get is about 6.32 seconds, which is far greater than 3 seconds needed. However, the good point is that we are able to reduce the steady state error to 0%. You see here the final value is 1. So we have 0 steady state error. As we have learned previously, when we introduce PI controller, the system type will increase by 1, and you know that for the step response, the system type 1, 2, 3 and greater will yield 0 steady state error. So in this case, we can try to increase, for example, 0.1, 2.1. So 2.1 or 2.09. For example, uh, what we get here is 9.97%. So at this point, again, the TP is 6.15 seconds, which is greater than 3 seconds. That is far greater than the design requirements, the 3 seconds needed. So I think this is the best that we can offer from the PI controller. So the next one, okay, we have, the next one we can try to use the PD controller. However, the PD controller approach is a little bit different from the previously we have done for P and PI controller. So I will explain the PD controller setting in the next video.